What's up, everybody? Welcome to Earth Science. So you should have gone through those other two videos quick, and this one's gonna maybe just hash some of the same stuff out, honestly, but take it a step further and just get a few ideas down on paper, and of course, a few questions. See how you're doing. All right. A lot of times in notes, I put this up at the top. I suppose it looks like boring teacher speak, and that's kind of what it is. These are the state standards. This is what New York State is telling me to get out to you guys, which also determines what kind of stuff's going to be on the regions. So sometimes I like to see them and have you guys see them because it just shows that we're on the right path. Stars form when gravity causes clouds of molecules to contract until nuclear fusion of light elements into heavier ones occurs. We're going to look at that for sure. Fusion releases great amounts of energy over millions of years. The stars differ from each other in size, temperature, and age. We're going to open that door today, but really analyze that a bit more in the next lesson. Our sun is a medium-sized, kind of normal, boring star within a spiral galaxy of stars known as the Milky Way. And our galaxy contains billions of stars, and the universe contains billions of these galaxies. And those are the ideas I was throwing out there in the first one. So let's do it. If we're going to have all of this, first we have to form a universe. And if you've never heard of this before, the idea we have for that is Big Bang Theory. All right, evidence for this. I'm actually going in a slightly different order this year. So I usually do that first, which makes sense, like invent the universe first, right? We're going to jump in this year first with stars and then work our way to that. So we're going to, for just a minute, skip that, but note that that's going to be important when we do that next lesson. So we got ourselves a universe, right? We did it. And that was a long time ago. Like when we talk about, this is a way I try to fool people. I'll say, how did the planet form? And people always want to jump to, oh, Big Bang Theory. Big Bang Theory gave us the whole universe, but then a whole lot of stuff was happening for a really long time, like somewhere in the ballpark of 10 billion years. We had in between the Big Bang, the beginning of the universe, and the formation of the star that we live around. So, giving ourselves a cosmic address here, we live in a village called Pulaski, or work and educate, which is in a state called New York. And if you get the idea of what I'm working on here, I'm going to go from the closest and zoom out, 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 which is in the USA on planet Earth. And planet Earth is one of 8 planets and Pluto and its dwarf planet friends in the solar system. We don't really have a special name for the solar system, like we never called it something other than the solar system. That's what it is. The solar system is one of many stars in the galaxy. We do have a name for this one, Milky Way. And there are lots and lots and lots of galaxies in the universe. Are there possibly lots and lots and lots of universes in some kind of megaverse? Possibly. But as far as we can observe, as far as we know, that's the biggest container we have right now until you find folks go and become physicists and make the next great discovery. Our galaxy, and we mentioned this in a previous video, is a spiral galaxy containing billions of stars. And it's kind of shaped like this. Then there are billions of galaxies in the universe. Just an outrageous amount of space, terrifying amount of space. As far as we can tell, kind of shaped like this. Now, the thing is that the galaxy is so big, we can't do like the selfie image. You know what I mean? We can't get far enough away to do one of these, take a picture of myself. We are like to get outside of even our solar system takes a tremendous amount of time. We'll talk about the Voyager satellites. They sent those out in like the 70s, and they're just now towards the edges of our solar system. Pluto and all of those. That's a long time ago. In terms of human lifespans and technology and what we got. So to consider that amount of space that we traveled, like since we sent these rockets out the satellites out in the 70s, it's too, like, the scale of this, we couldn't even see that distance, right? It's too small. So there's just no way that we can get far enough away to turn around, point back at the Milky Way and say, here's a selfie of us. So how do we know? We've made observations of kind of what we can see, Again, it's like living in a disk. It's like living in a frisbee. You can see around it, but that's you're seeing it from the inside. And we've made observations on what other ones are out there that might look kind of similar and mashed it up and gotten pretty close to that it's a spiral galaxy. Is this exactly perfectly what it looks like? No. This is besides just being some crappy clip art I stole from the internet, it's also like even our best estimation is going to be imperfect. Now, with all that space out there, this is called, you don't have to necessarily have this down, but this is called the Drake equation. It looks complicated, and don't worry, we're not getting into any math, but it's an idea saying that, and I think I mentioned this in the last video too, how many stars are out there? How many could possibly potentially have life? How many of those would possibly develop life? How many of those would possibly have intelligent life? And even though these are all numbers that are like tiny, 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 tiny fractions, there's so many stars out there that this would end up still being a pretty large number of planets. So it's mathematically likely that there are other intelligent um, species out there on different planets. But again, just plain too far to be able to get to or communicate with. All right, so how did this thing get here? Solar nebula theory. So we would begin with this cloud of gas and dust. We're going to have to put a little bit of text in here. This might take a minute. Again, you're on YouTube. Feel free to pause when the time is right. So we get these interstellar clouds of gas and dust. They're visible today. So interstellar. Go a little bigger here. Sorry if these are small. And remember, you can zoom. Get a little smaller. Interstellar, fancy word for just like in between stars, like out there in space. Don't panic too much about that. Out in space, clouds of gas and dust. The term for that, and this will come up as a vocab word, if I can make it a brighter color, is a nebula. Okay, so the one red, the word one black, that's fine. Interstellar clouds of gas and dust called a nebula. All right, again, observable out there. And at some point, the one that would eventually form our sun, our planets, and essentially the atoms that are in your body right now, all of that stuff had to be kind of floating around in that nebula until a point where it got dense enough. If you remember our concepts of density, it got dense enough where things within it could start to be gravitationally attracted to each other. Gravity, we're going to play with a little bit. We don't really have to get too detailed. You're going to do it more in physics. Gravity is a function of your mass and your distance. So I've got this mass, this much affinity, right? As a function of that much mass and the mass of the planet, we're gravitationally attracted to each other. Now the planet's huge, so it pulls down with a reasonable amount of force, given my weight. I'm gravitationally attracted to this water bottle too, because it has a mass, I have a mass, and there's a distance between us. But we're not massive enough to really be able to notice this. In these nebulas, once it gets dense enough, it starts to collect and condense and collapse. And what happens is that the most massive stuff starts to build up, and then it's more massive, which means it has more gravity, which means it pulls more stuff in, which means it's more massive, which means it has more gravity, which means it pulls more stuff in. So that's a positive feedback loop, we call it. The bigger it gets, the more it has an ability to pull stuff in. So the bigger it gets, so the more it has an ability to pull stuff in. You can say that over and over and over again, really, until you clean up this whole entire mess and form a solar system. So in the early phases, it would have been what's called, this is a less important vocab word, a protostar. But eventually what would happen, I'll come back and I'll highlight like in a different color what the really important vocab words are here. Nebula is, protostar isn't. Eventually what would happen is a vocab word that will be important is fusion. And in our star, in our sun, it's hydrogen plus hydrogen, and that's an equals. H plus H gives you helium and energy. Now, this is a complicated physics to get down nuclear fusion, how you can take two atoms and mush them together and like change atomically what's going on. Take those, if you know what helium is, just it's on the simplest one on the periodic scale. Take those and mush them together and turn it into a different atom. It releases energy. It's way complicated physics, and it's definitely something we don't need to get into. That's the good news. But What do we have to know? Go back to the state standard. Uh, fusion basically powers stars, and fusion releases great amounts of energy, and we'll be good with that. Okay. If you want to get more into that, we can talk more about it, but it gets pretty complicated pretty quick. Around that are going to be is a protoplanetary disk. I'm not even going to write that one because that won't show up. A protoplanetary disk. That'll be when there's still a whole bunch of chunks and asteroids that are still banging around and smashing into each other, and eventually give it enough time, and the planets will clean up their own orbits through constant impacts, and adding to the planets. The only one that didn't get cleaned up is the what's still the asteroid belt right there. So you can kind of picture the asteroid belt as being what it would have looked like earlier in its origin. But now we've got the 8 planets, the asteroid belts, and a whole bunch of dwarf planets out of that, all spinning around this. And the spinning's part of it. With the collapsing, there's spinning. Conservation of angular momentum is the fancy term. And as this gets larger and has more gravity, the spin around it, everything kind of equals out, giving us what we have today. Now, this has been a long trip of trying to figure this all out. But again, things that are observable through the rest of the universe today. So yeah, important words in that. If you want to circle in a different color, nebula, you're going to see fusion, you're going to see. So let's just make a note here. Fusion is the thing that powers stars. Okay. Stars change through time. Our sun will eventually run out of its fuel, hydrogen. It will expand its size pretty much to a point where it's going to like consume the Earth, and that's it for everything that's ever happened. Oh, gone. We got plenty of time left, but that'll be that. That's the end of it, right? And all stuff that's observable again today. We see that stars go through this life cycle. They're born out of these nebula. They have different paths based on how much mass there is and what kind of materials they're fusing together. And then they go away. They die. They burn out. Okay. We're gonna have to learn this. This is a tiny, tiny, tiny version of a reference table. We're gonna have a full page one and really figure out how to organize and categorize all these stars. The HR diagram categorizes stars as they appear, like right now, today. However, stars change through time. The two quick diagrams, and then we'll wrap this up. Sorry, I think I'm going a little longer than usual. These were both, I actually scanned these both out of Regents questions. So these are the kind of things that appear on Regencies. Now, the good news, you do not have to memorize these. All we really have to know is that stars change through time, they evolve. And it can be based on their mass and what things they are fusing together. So in both cases, we're starting with a nebula, and then it moves into a protostar, which is just early star, proto something like a prototype car, into a main sequence star. We don't know what that means yet, but that's okay. Hang tight. We're going to figure that out as we move forward. And then into these supergiants or giants, depending on mass. More massive, less massive will send you down different paths. Supergiant, supernova, black hole, giant nebula, white dwarf. If that all sounds pretty confusing, again, don't panic. It's nothing you have to memorize. And we haven't covered what these stars are yet. That's going to be the next lesson. We'll do that. But for now, yeah, stars change through time. And we just happen to be alive on this planet. And I think we're somewhere in the ballpark of halfway through the lifespan of our sun, our star. Its fate is down here along those more medium mass ones to be a giant, white dwarf, black dwarf. But we won't make it past that stage. We being the planets. All right. There's the standard one more time, just in case you want to use it to cheat on 4 quick, easy questions, just to see if we were listening what's going on. So I'm going to leave you alone to fill those out. Do that, and you can move on to the next lesson. Thanks. How long do we go? Way too long? Oh, 14. Thanks for hanging in there, folks. Talk to you soon.